All right, let's get started. Good morning. So, reminder for the exam next week, next Thursday, 6:30, same time as the other two, same place, same seating location within the Hall of Music. As usual, make sure you know where to go. Look up the section if you forgot. If you get lost, look for your TA. If you can't find your TA, look for me. And let's look a little bit ahead to what's going to happen today. We're covering one more new lesson, and also next Monday. So there are two more lessons that are not going to be exam 3. And then the Wednesday before the exam, we'll do review, like we've been doing for the last two. And then Thursday, there is a review recitation and the exam that night. Okay, there is class after the exam. Friday after the exam, there's a class. Remember, instead of taking that day off, we moved it to the Monday of Thanksgiving break. All right. Okay, so today we're going to be looking at section 4.9. We'll be looking at antiderivatives or antiderivatives, however you want to say it. Essentially, you've been learning all about derivatives, how to take derivative of something. From this point on, we're going to undo all of that. We're going to learn how to undo the process of differentiation to get back to the function that gave us a certain derivative. Okay, so many of you know that the Greek prefix anti or anti, tomatoes, means the reverse of something or against or opposite of something, right? So when you look at the antiderivative, it's literally the reverse of differentiation. In other words, if we have the derivative of something, somehow we have the derivative of a function, we want to find out what function gave us that derivative in the first place. So for example, if you have the derivative of something equal to cosine, you know it came from a sine, right? Because derivative of a sine is cosine. We'll start with the simplest reverse of differentiation. We'll look at the power rule. That was the first differentiation rule we learned. And we'll look at the reverse of that. Essentially, we do everything backwards and the opposite of what we have been doing. So let's write down how we take the derivative to start. We'll look at a very simple one. Let's say x squared. We know the derivative is 2x. Okay, let's write down what actually happened, and then we'll analyze how we can undo that. So in words, this came about because what did we do? We reduce the original power by 1, right? That's how we went from square to first. Then what happened is we multiply by the old power. Even though we brought it down and reduced the power, but in terms of basic operations of mathematics, what we actually did was reduce the power by 1 and then multiply by the old power. Okay, let me underline a few words here. Now let's find out how we can go back. We're going to undo everything, do the opposite of all these things I just underlined. We know this thing came from that, right? F of x. So what did we do? We look at what we started with. First, we increased the power by 1. Okay, instead of reducing, we do the opposite. We increase the power to go from 1 to a 2. Then, instead of multiplying, we're going to divide. Instead of multiplying by the old power, we're going to divide by the new power. Right? So here's what happened. We increased the power by 1. It went from 1 to a 2. Then, to get rid of that 2 in front of it, we divided by the new power. Right now it's a 2. Dividing by that, the 2 went away. And that gave us the x squared that we were looking for. So in general, in words, the antiderivative of x to the n is we increase the old power by 1. So whatever n I started with, I add 1 to it. Then I divide it by the new power, n plus 1. Okay. Okay, let's try that on something very simple, and then we'll look at a few more complicated ones. Oh, by the way, this is very important. Anybody see a potential problem with this thing right here? What happens when n is minus 1? Yeah, this expression doesn't make any sense. So this rule only works if n is not minus 1. There's a different rule for that. We'll get to it near the end. But for now, just remember that for the power rule only applies if n is not equal to 1. Okay, a simple one. So something has a derivative of 3x squared. What gave us that derivative? Let's apply the rule. This one we could actually just look at it and know it's x cubed. But let's go through the rule here. Remember that 3 constant multiple does not participate in differentiation. It also does not participate in reversing the differentiation. The 3 sits there. Here's the x to the n. So we add 1 to the existing power. Then we divide it by the new power. Existing power is a 2. We add 1 to that to bump it up to x to the 3rd. And then we divide it by the new power after we added 1. So we get 3. We get the 3's go away, right? I'll write out the steps. Of course, you can always check. Whatever I just got, if I take the derivative of that, I better get what I started with, because that's literally what we did. We undo the differentiation. We get 3x squared, right? As we should. So this matches that. Therefore, it's okay. Okay, a very, very simple rule. Now we're going to add one thing we need to look out for here is this is one of the many, many possible functions that gave us that derivative. But note that x cubed is not the only possible antiderivative of 3x squared. Okay? What else could it be? Besides x cubed, what else could it be? How about x cubed plus 1? Would it have the same derivative? How about x cubed plus 2? X cubed minus pi? X cubed plus 100,000 e? They all would have the same derivative. Right? See that? Question? That's right, that's right. Yeah, but you're going a little bit ahead here. But for now, you got the main idea here. We don't know what it would go through. Okay? So the point here is because x cubed plus 1, x cubed minus 3, x cubed plus pi, etc., all have the same derivative. Of 3x squared. In fact, x cubed plus any constant we'll call that constant c. Whatever the constant c is. Will always give us the same derivative. Okay, so we need to be able to capture that potential constant that was added to it or subtracted from it. So we say the most general antiderivative of x to the n is add 1 to the old power divided by the new power plus some constant. We use that c to denote that constant. Essentially, without any more information, we don't know what constant could have been there. We have to account for the possibility that there was a constant. So we always put just something to represent that. This constant here is called a constant of integration. It represents some possible constant that could have been there, but it would have disappeared once we take the derivative of that thing. All right, does that make sense why we add a plus c? Yes? Wake up, wake up. Yes, no? Good, good. Good. Thank you. All right. Now, if you got multiple things added to or subtracted from each other, you just deal with them one by one, like how we take the derivative of those things. So for example, suppose some mysterious function has this as a derivative. Let's find the most general. F of x that gave us that derivative. If you were taking the derivative of this thing, then you would take the derivative individually. Same thing here. If you're undoing that, you would undo it individually, one at a time. Okay, so 9x to the 9, remember that multiple of 9 doesn't participate. For x to the 9, we add 1 to the existing power, divided by the new power. We hold off on the c for now. We keep going. Minus 4 times x to the 6, we add 1 to the existing power, divided by the new power. Continuing with 12x times x to the 3rd, add 1 to the power, divided by the new power. Okay, now we get to this last one here. What power of x did this 10 have? 0, right. We repeat the same rule. It had a 0 to start, right? So we add 1 to the existing power. It has 0 to start. Then we divide it by the new power. So let me write down what's going on here. This 10 really is 10 times x to the 0th power. Right? It had a power of x, so we just carry on the same rule. Now at the very, very end, remember, some constant could have been there in the first place, but it would have disappeared when we take the derivative. So now we add a constant of integration plus c. You only need one of those, but you have to have one. Without it, it would not be the most general possible function that gave us that derivative, but just put a plus c there to account for potential possible constant. Okay, let's clean this up. 9 over 10, x to the 10th, minus 4 over 7, x to the 7th, plus 12 over 4, x to the 4th, minus 10x, plus some potential constant. All right, how do I know if I did this right? Take the derivative of it, right? If I take the derivative of this, I better get that. So let's check that. So what do we get? We get 9 over 10 times 10x to the 9th minus 4 over 7 times 7x to the 6th plus 3 times 4x to the cubed minus 10. A constant, regardless of what it was, it would be a constant with no x whatsoever. So it would always end up giving me a 0 derivative. So we get 9x to the 9th minus 4x to the 6th plus 12x cubed minus 10. Check that. Yep, that's what we started with, so we are good. Okay? You always have a way to ensure that you did this correctly by taking the derivative of something. If it's not the same thing as you started, no, you did something wrong. Go back and check. Questions? We'll get to them. That's right. They may look different, but they would. If you have all the trig identities at your disposal, you should be able to make them look the same. But you're right. Trig is kind of a potential difficult situation there. They can look. The same trig function can take on many different kinds of forms by using various trig identities. Now, one easy way to check is just to plug in a number for x. But that doesn't guarantee that it's correct. Right? If you plug in 10 different numbers and they all match, then that gives you a more of an assurance. But that's one way that you could check that. Those are complications that we'll deal with later. Okay, let's check out this one here. So something has a derivative of 7 plus x squared over radical x. We'd like to find out what gave us that derivative. Just like when we first started learning differentiation, we wanted to put everything in terms of x to the n. That's what we're going to be doing here. Somehow put this into a form kind of like in the last example, and then we can deal with those terms one by one. There's only one thing in the denominator, so you simply divide everything on the top by that, one at a time. The first one is 7 times x to the negative 1/2. The second one is x to the positive 1/2. The last one is x to the positive 2 minus 1/2, so that's 3 over 2. Okay, we haven't done anything yet other than just rewriting the function into a form that we could deal with. So this is fundamentally no different than the last example. Now we apply the rule. 7 doesn't participate. Add 1 to the existing power. If I add 1 to minus 1/2, I get positive 1/2 divided by the new power. Same thing here. Add 1 to 1/2 divided by the new power. Add 1 to the new old power. 3 over 2 plus 1 is 3 over 2 plus 2 over 2, and that's 5 over 2. Okay? Is that it? Yeah, there could have been a constant somewhere that disappeared from the differentiation when we went to here. So we need that constant to account for the possibility of that. Some unknown constant. Okay, now let's clean this up. 7 divided by 1/2 is the same as 7 times 2. So that's 14 x to the 1/2. over 3 over 2 is the same as times 2 over 3. Over 5 over 2 is the same as times 2 over 5 plus c. Of course, if you take the derivative, you should get this. And then from there, you can do all sorts of things to put it back into that form. You should be able to match one of the many different forms that a function can take after you take the derivative. All right, this next one is the same idea. Just like the last one, we want to make this into additions and subtractions of x to the n. And if we have that form, we can deal with any complication, no matter how complicated that may look like. All right, so let's multiply this out. Let's multiply these two things out first. We get 9 minus 6x plus x squared. So this is equivalent to 9x minus 6x squared plus x cubed. And now this is no different than the last two examples we've looked at. Exactly the same situation. Here's a 9, doesn't do anything. X to the first, we add 1 to the power, divided by the new power. Minus 6 doesn't do anything. X squared, bump the power up, divided by the new power. X cubed, bump the power up by 1, divided by the new power. Plus some mysterious constant that could have been there. Even 0 is a constant that was there, so that plus c takes care of all possible constant. Clean it up. And there we go. Okay, it's pretty easy stuff. Simply undoing what we already know. And as usual, if you want to be sure that you got this correct, just differentiate that, take the derivative. It should match that. You may not be able to match the original form it took, but you should be able to match the intermediate form that we used to get to this point. And that's the same story with trig, right? What? Oh, it should be what? 3, right? Why did I write 6? I don't know. Okay, thank you. 2, 3, 4. Good, thanks. That looks like a 30. That's a 3. Okay. All right. Okay, so that's how we handle x to the n. Of course, you also need to remember how to undo the derivative of other things. Let's look at the x to the n with n being minus 1 to start. That rule, remember, does not work. It doesn't give us anything that makes sense if n is equal to minus 1. So let's start by looking at what x to the minus 1 would turn into. Okay, we've seen this before. One of the functions that we've dealt with has a derivative of 1 over x. Do you remember what that was? What function has a derivative of 1 over x? Natural log, right. We got to be really careful with when we do apply the rule here. For this to make sense, x has to be greater than 0, right? Because natural log of x doesn't make any sense when x is negative or 0. So therefore, we have to be sure that we have a meaningful number here. When you just have natural log of x, that x could be anything, just not 0. But when you turn it back into it, you have to have something that makes sense. So what we do is we put an absolute value around that x, just to make sure that is meaningful. It's needed because we don't know what x is in 1 over x. If you just say 1 over x without telling us anything in addition to that, well, we know it could be negative, it could be positive, it just cannot be 0. So therefore, the antiderivative of that has to be written as natural log of the absolute value of x. That's just to make sure that in the end that makes sense. Other things we've seen before. So if we say that the derivative of something is cosine of x, then what function gave us that derivative? Sine, right? Sine. Sine plus some possible constant. What about if something has a derivative of sine of x? What gave us that derivative? Right, negative cosine. Good. So with trig, you got to think backwards. There's no rule like a power rule. You just have to remember how to go backwards from the trig functions. Another example here. If the derivative is negative cosecant squared, then what's the original function? Remember this one? I don't know. It's a negative square. Let's make the, sorry. Sorry, let's try that again. If the derivative is negative cosecant squared, what gave us that derivative? The fact that it's a negative, remember, it tells me that we must have differentiated a co-something, because co-something always has a negative derivative. So what co-function has a derivative of negative cosecant squared? Cotangent, right. Okay, so with trig, you just have to think backwards. You have to think backwards to what gave us that derivative, and so on, etc. Right? We can go over all of that, but I think you understand the idea there. Polynomials are simple. X to the n is simple. We have a rule for that. Exception to the rule is 1 over x. That's natural log of x. And trig, just have to think backwards. Okay, let's check out this next one. You can do the same thing if you have the second derivative of something. So let's say, suppose we have a second derivative of sine of x plus cosine of x plus 3x. And let's find out what gave us that. So some function that when we differentiate twice, we end up getting this thing. So all you have to do is just go back one step at a time. Let's go back to the first step. This is the second derivative. Let's undo one layer of that. First, remember, what gave us the derivative that's equal to sine? Well, cosine has a derivative of negative sine. So if we started with a negative sign, a positive sign, we must have differentiated a negative cosine, right? So the antiderivative of sine is negative cosine, because the derivative of that is this. Cosine must have come from a sine, a positive sign. And then 3x squared turns into 3x turns into 3x squared over 2. And then one mysterious constant that we don't know what it is yet. Okay? Now let's do one more time. We're going to go back one more time. All right, so negative cosine. What gave us that as a derivative? Negative sine, good. What about sine here? Negative cosine, right. Here, same thing. 3 over 2 doesn't participate. We add 1 to the existing power of x squared divided by the new power. What about this c? Cx, right. Right? It's a constant. Think of it as a 2. What would have a derivative of 2? 2x. It's a constant. So what would have a derivative that's equal to c? Cx. And then we need one more constant. Everybody see that? Each time you undo that differentiation, you need one more constant. Let's call that d. Is there a question over there? Everything okay? The second constant of integration, because we reversed differentiation twice. Each time you undo that, you have to have one constant. So let's clean this up just a little bit. So what's this equal to? 1/2 x cubed plus cx plus d. All right, does that make sense? Any question? So if I start with the third derivative, in the end, I would have 3 unknown constants. If I started with the fourth derivative, I would have 4 unknown constants. If I started with the nth derivative, I would have n unknown constants at the end. To figure out what these constants are, you have to know a little bit more about the function. find the value of c or any other constants, we need to know at least one point on the graph of f of x. If you give me the derivative, I can undo that, but I can't tell you what the derivative would be, because the derivative deals with slope. And you can have the same graph with different up and down location or left and right that all have the same slope, right? You have to tell me what point that graph goes through for me to tell you what that constant is. So I'm going to use a very simple example to show you the idea behind that. I have a function whose derivative is 2x, and I know that whatever this original function was, it had to go through the point 0, minus 3. Okay? So what this means is that f of x goes through the point 0, comma 3. When we apply the power rule, we get x squared plus c. So at this point, this represents all parabolas. With the vertex at 0, c, right? So these represents all possible parabolas that have different vertices. Until you tell me what this parabola has to go through by providing me with that piece of information, I can't tell you which one of these we started with. So let's say this point right here is our 0, minus 3. Right, then we only have one possibility left. Once I know one point it goes through. Okay? If I start with a second derivative, then I would need 2 points that the function goes through. Like in the last example, we would need 2 points. You need to tell me one point on the graph somewhere and 2 unique points. They cannot be the same point. Each unknown constant has to come from either 2 points or a point on the derivative. So anyway, here, we have this. We also know this one point. So that means when x is equal to 0, y is equal to minus 3. Substituting that information into here, we get minus 3 is equal to 0 squared plus c. Well, all that says is that minus 3 is equal to c, right? So f of x must be equal to x squared minus 3, which represents that one and only one possible parabola that can exist, can fit this description. All of these guys have the same slope, 2x. But The only one that has that slope and goes through this point is that particular one. Okay, let me show you one example with two unknown constants. We'll make the starting very simple, minus 9.8 as the second derivative. So that's the kind of thing we need to have. If you have the second derivative, you want to undo the differentiation twice. You either need two unique points on the original function, or you need one each on the derivative and the original function. Let me write that down. Somehow you need two pieces of information to account for the two unknown constants that are going to fall out of that. All right, so let's undo the first layer. If f double prime is minus 9.8, then f prime must be minus 9.8x plus the first unknown constant, c. We know one point on f prime. So we can use that information to find c before we proceed, right? We know f prime of 0 is 5. So that means when I substitute 0 in here for x, I get 5 on the left side. And I see that 5 is equal to 0 plus c. That means c is equal to 5. Now I know what c is. I get it by putting the value I know for sure before I do it one more time. Then we undo one more layer of that. Reversing one more layer of derivative, we get minus 9.8 x squared over 2 plus 5x plus the second unknown constant. Now we use the point on the original function. Find d from f of 0 is equal to 7. So we see that 7 is equal to 0, 0, d. Then we update what we know. What did I do? Nothing. All the buttons are down here where my hand is. It's really not very good. Anyway, that's what we get, right? You need 2 points on the original graph, or 1 point on the derivative and 1 point on the original graph. If you have triple derivative, then it gets more complicated, but the same idea applies. All right, that's it for today. Have a good weekend. See you Monday.
just that like I guess always the calculus like function just gets bigger as there's more terms. Yeah. Okay.
Um, so I didn't do, or I didn't really understand a lot of the optimization homework that I was doing, and I didn't get enough help in the rest of the class. So where would you say I should look for more optimization specific problems? Just out of the textbook, just do the homework for yourself. Okay, and then just like look for optimization problems. Okay. Nice.
Hi, I had to reschedule the exam last time. I think I'm gonna have to do it again.